integration by substitution with the power rule. If your main function is of the form f of x raised to the p, in order to determine if we want to use integration by substitution, we want to take a look at what the inside function is. So we isolate f of x, and then we want to determine if the derivative is also present in the problem. If it is, then it's a good candidate for integration by substitution. Example 5. Here we see we have two different things in parentheses. What we want to do is we want to consider the function that's raised to the highest power. So here my highest power is 15. So I want to look at the function that's inside the parentheses. Here, I see that function is x to the fifth minus 3x squared plus 1. The derivative of that is 5x to the fourth minus 6x. I notice that that is also part of my antiderivative multiplied in front. So I know this is going to be a good candidate for substitution. So again, remember, when I do integration by substitution, I'm undoing the chain rule. So I need to think about what the original inside function was. So remember, the original inside function is the function that has appeared and is now being raised to a power. So when we do our substitution, we want to pick our u to be the inside function, which again is the function raised to the power. Now, we have to be a little careful about this because our u is just that function. It's not the power. So we ignore the power when we're picking our u here. So we get x to the fifth minus 3x squared plus 1. It's not raised to the 15th. The u is just the inside function. So our du, or the derivative of that, is 5x to the fourth minus 6x. So du, we need to multiply the dx up, and we get 5x to the fourth minus 6x dx. So again, we need our du and our u in order to be able to complete our substitution. So again, finding our u is one of the hardest steps of the problem. Once we can find that, we can find the other pieces we need. So our u, again, was the function that's being raised to the power, but without the power included. So now we want to turn our antiderivative into something that's all in terms of u. So our first step is to plug in what u equals. So we're going to plug it into the parenthesis that was raised to the power. That gives me u to the 15th. Then I want to look at what's left. So here I have 5x to the fourth minus 6x dx. I need to compare that to my du. If it's different by a constant, or if it's exactly the same, then I'm good to go. If, however, I differ by a function, that means that I probably don't want to be doing substitution here. But when I look, I see in this case that my du is exactly what's left here in my antiderivative. So instead of those terms, I can substitute in a du. So I have the antiderivative of u to the 15th du. So we're going to use our power rule here. So we're going to add 1 to the power and divide by the new power. So that gives me u to the 16th over 16. But I don't want a u in my final answer. I want everything back in terms of x's. So I need to substitute back in what u represented, which was x to the fifth minus 3x squared plus 1, all raised to the 16th power divided by 16 plus c. So I've successfully completed now my first integration by substitution with a parentheses raised to a power. We want to look for patterns on how this process works and how we identify things and how we work with this type of function. So let's look at another one. Example 6. The antiderivative of x cubed times the square root of x to the fourth minus 3. So whenever we have square roots, the first thing we want to do is we want to turn our square root into a power. So here, my first step is going to be to rewrite this. So I have x cubed times x to the fourth minus 3 to the 1/2 power dx. Now that I've rewritten it as the 1/2 power, I see that I have a parentheses raised to a power. A quick look at the function inside that parenthesis, I see I have x to the fourth minus 3, and I know the derivative is 4x cubed. I look at what's outside the parenthesis and I see an x cubed function. So that's promising that I should be able to use integration by substitution because the functions are going to be different only by a constant. But let's do out the side work to make sure it works. So again, my u is going to be what's inside the parentheses, not the power itself. So x to the fourth minus 3. My du is going to be the derivative of that. So that's going to give me 4x cubed. And so here I multiply up the dx and I get 4x cubed dx. So again, I need a u and I need a du to attempt my substitution here. So first I want to plug in my u into the parenthesis that was raised to the power. So that's u to the 1/2. Then I want to look at what's left and compare. So what I have in my antiderivative is x cubed dx. If I come over here to my du, I see I have a 4x cubed dx, but that's only different by a factor of 4. So I can actually divide both sides by 4, so then I get 1/4 du equals x cubed dx. So here, now I have it matching exactly what's left with the antiderivative, x cubed dx. So instead of an x cubed dx, I'm going to substitute in a 1/4 du. Now that I've done that, I'm going to pull the 1/4 out front because it's a constant multiple and it's going to help me keep my fractions straight. You don't have to pull it out to the front, but I think it helps. So now I know that my answer is going to be 1/4 times the antiderivative of u to the 1/2. So the antiderivative of u to the 1/2, I need to add 1 to the power. So that's going to give me u to the 3/2, and then divide by the new power. But if I divide by 3/2, that's the same thing as multiplying by 2/3. So now, for my last step here, I need to do two things. First, I want to simplify my fraction. So I have 2 over 12, which is the same thing as 1 over 6. And then I need to substitute back in for u. So I go to what u equals, and I substitute back in x to the 4th minus 3, and then I raise that to the 3/2 power. So my original function, or my antiderivative here, was 1/6 x to the 4th minus 3 to the 3/2 power plus c. And I know that if I were to take the derivative of this function using the chain rule, I would get back my original function. So again, I was able to do this work and I was able to look at these pieces because I'm undoing the chain rule and I'm trying to understand what the original inside function was. I call that u, I do my steps to find du, I substitute in, and once everything is in terms of u, I can hopefully find the antiderivative from the antiderivative formula chart. Let's try another one. Example 7. So here, this looks fairly complicated. We have e's and we have trig functions. And again, we have two parentheses. So we have to figure out which one we should pick to be our u. So again, we're looking for the parenthesis that's raised to the highest power. So here we see that one of the parentheses is raised to the 8th power, which means my u is going to be the function inside that particular parenthesis. So I'm going to go ahead and I'm going to write down my u is e to the x plus cosine x, because again, that's the one in the parenthesis that's raised to the power. Now I want to find my derivative here. So the derivative of e to the x is e to the x. The derivative of cosine is negative sine. So now to find du, I need to multiply the dx up. So I get e to the x minus sine x dx. So now I have my u and I have my du. So I can start my substitution. So first I'm going to substitute in my u. That's going to be raised to the power because that's how I picked my u. So I have u to the 8th. Now I need to look at what's left. So I have e to the x minus sine x and a dx. If I go to my du, I see that that is exactly what I have for my du. So that's fortunate. So that means that instead of that function, e to the x minus sine x dx, I have du. So I'm going to substitute that in, and that leaves me with the integral of u to the 8th du. So now I'm going to use my power rule, and I'm going to add 1 to the power and divide by the new power. So that becomes u to the 9th divided by 9. But I don't want a u in my final answer, so I need to substitute back in what u represents. So that's e to the x plus cosine x, all raised to the 9th power divided by 9. So my antiderivative I now have, and again, if I took the derivative of this, I would get back the original function that I was evaluating, because that's how we define antiderivatives. Let's try one more of the parenthesis to a power type of integration by substitution. Example 8. So again, we see that we have two functions here that are each in parentheses. So again, we have to be mindful to pick our u to be the function that's raised to a power. So between these two parentheses, the function that's raised to a power is the 3 to the t minus t cubed. So that's how we're going to pick our u. And again, our u does not include the power, it's just the inside function. So our du dt is the derivative of u, which is going to be 3 to the t times the natural log of 3, which is the base here, minus 3t squared. So our du is 3 to the t times the natural log of 3 minus 3t squared dt. So again, we want to start by substituting in our u. So our u is going to go in here into the parentheses, and we get u to the 2/3. Now we have to look at what's left. So we compare our parenthesis that's left with our du. So our parenthesis says 2 times 3 to the t times the natural log of 3 minus 6t squared. Looking at what we have left and looking at what's over in our du, I notice that it's only different by a factor of 2. So again, I can multiply both sides. So 2 du is going to equal 2 times 3 to the t times the natural log of 3 minus 6t squared dt. So if I multiply everything by 2, then my functions match up perfectly. So instead of the parenthesis that's there, I'm going to substitute in a 2 du. So again, I'm going to pull my constant to the front. That's a matter of preference. You don't have to do that. But I find it's easier to do the algebra. So now we have a power rule here. So the constant multiple says that 2 will multiply our antiderivative. So if we add 1 to the power, we're going to get u to the 5/3 divided by 5/3. But remember, if you divide by a fraction, it's the same thing as multiplying by the reciprocal. So instead of dividing by 5/3, I'm going to multiply by 3/5. So simplifying my constants, I get 6/5. And now I want to substitute back in for u, because remember, I don't want a u in my final answer. So that means I'm going to substitute in a 3 to the t minus t cubed, all raised to the 5/3. So again, I found my antiderivative, and if I were to take the derivative of that function, I would be able to get back my original function that I started with.